I recently authored an article on Medium titled When Node.js I/O Blocks. And it talks about Node.js threading architecture and how is it a single threaded and how it is an asynchronous, non-blocking I/O. How does it achieve that in details? So I talk about the thread pool. I talk about how does it perform file I/O. I talk about how does it perform socket I/O asynchronously, such as UDP and TCP. I talk about how does it perform DNS queries through the thread pool. And I also talk about when exactly is it that Node.js blocks the execution from the user perspective. I thought it was an interesting read, and this is the audio version of this article. I'm going to publish the audio version on my podcast, The Backend Engineering Show, and the video and audio, of course, on my members only YouTube channel. I hope you enjoy it. When Node.js I/O blocks, written by Hussein Nasser on October 11th, 2022. Node is a non-blocking JavaScript runtime. You can simultaneously run an HTTP server, read files from disk, send UDP datagrams, accept TCP connections from clients, and still have room to execute JavaScript code operations without blocking. Emphasis on without blocking here. Most of these operations are known as I/O. I/O, or input output for short. You send an input to a device, a file, or a socket, and it replies back with an output. Node achieves a non-blocking I/O with mostly a single thread executed asynchronously using a library called libuv. The exception being DNS queries, which use a thread pool. This means when you use fetch or axios to make an HTTP request to a domain, the DNS resolution for that domain will most probably go through that thread pool, while the actual request itself, the HTTP request to the IP address, will be sent asynchronously on the main thread. So, when does Node block and when it doesn't? I attempt to answer this question in this article. Part 1. Socket I/O. When a backend application binds to an address and a port, it creates a socket. Attempts to connect to the socket will spawn connections that can be accessed through file descriptors. File descriptors are integer values representing TCP connections, UDP sockets, or even literal files on disk. When a client sends data on the connection, the server operating system reads the data from the NIC, or the network interface controller. Using the from and the to IP address and port, the OS maps the data to a file descriptor and puts it in the kernel buffer. It is now up to the application logic to explicitly read the data on the connection so it can be moved from the kernel memory to the application dedicated memory. Calling read from the application will do exactly that. Read here is an actual operating system call. And that's a very important thing. This is now Hussein. Now I'm not reading anything in the article. Read will move data from the kernel to the user space memory. And I never actually knew that actually this is happening. And now that my eyes are opened, a lot of things started to make sense in my earlier readings and analysis. This is all good and well when there is data in the buffer for that connection. But what if there isn't anything in the kernel buffer? The client didn't send anything yet. The read call from our backend will block because there isn't anything there. That's the definition of the system read call. Again, that's me now. I'm not reading anything from that article. I'll be jumping back and forth in the podcast to actually make commentary on my own article. It's pretty interesting. So you get more content actually when you're listening or watching this video. The read call from our backend will block. The OS will move the application process out of the CPU so the CPU can do better stuff. Because guess what? When you actually, that's me now again, when you actually make a call and that call is just blocked, sitting there, not doing anything, the CPU will not leave our instructionless process in the CPU. It will put more useful stuff. And that moving us from out of the CPU is very expensive. It's called context switching. Let's continue. I guess I'm jumping the gun here a little bit. The read call from our backend will block. The OS will move the application process out of the CPU so the CPU can do better stuff, while our app remains blocked until someone sends data on the connection. That is very interesting, really, right? We are at the mercy of actually someone sending data. Otherwise, we will be completely blocked. That's by design. Okay? This behavior is called synchronous I/O. What we just described is called synchronous I/O. And synchronous I/O is always blocking. And it is mostly undesirable because guess what? Not only the CPU has things to do, you can't block the app just because we're not doing anything. The app can do other stuff while it's waiting. The app also has other things to do, technically, right? And this is where the asynchronous I/O was born. So all that paragraph was discussing asynchronous I/O. Asynchronous I/O was designed initially based on the idea of readiness and eventing to solve this exact problem. This is at least in Linux, if you ask me. This is a knee-jerk reaction, if you ask me, actually, in Linux, because it was we were quick to jump in to solve that exact problem, right? It says, okay, we are just solving the readiness model for sockets. What does that mean? We're going to split the I/O into two calls. That's how that was initially solved. A call called select to check if the file descriptor is ready. That means has something to read. And a second call to perform the physical actual read. And if we call select and it says, hey, you're not ready, we're just gonna turn around and call it again, right? It says, hey, are you ready now? Are you ready now? Are you ready now? Or just, you know what? I'm gonna call you now and let me know when you're actually ready. Let me know when you have data. And I'm gonna, when you have data, I'm gonna call read. And in that case, I know that I'm not gonna be blocked. And that's the trick here. If select returns ready, we know that read will not block us. Else, if select returned not ready, our app can move on to do something else meanwhile. Variations of this model were developed to improve asynchronous I/O, most popular being epoll in Linux. Details here are irrelevant for this post, but select, poll, and epoll are based on the idea of eventing. Here are a bunch of file descriptors. Tell me whenever any of them are ready for me to read. That's the idea here. Nothing to do with actual completion, but it's based on readiness. Are you ready for me to actually do the task? This is as opposed of the other model, which is the completionist model, which we're going to talk about in the end of the article. Now, this is a quote. We could have modified the read function to no op when there isn't anything in the file descriptor instead of blocking. My guess is this would have created bad pattern where the app makes a lot of unnecessary calls to the OS, which will hinder performance eventually. I could argue the read calls blocks on purpose because of this particular reason. Part 2. File I/O. Reading and writing to files didn't benefit from asynchronous eventing model described above because there are no events when it comes to files. Unlike network sockets where the app can be notified when data arrives to the socket, the file data is always there. I suppose you can use the model to listen to changes on the file and notify the app, but use cases for that are limited. Calling read on files will still block, but not because of absence of data, but because it just takes time to read from the hard drive or the SSD. The read transfers the requested blocks from the disk controller to the OS cache and then to the application. In the few milliseconds that the read is blocking, the app could do other things. So an asynchronous model for reading files is still desirable, especially for database people like us. If the requested portion of the file happened to be in the OS cache, the read will be faster. Now, whether you consider the read to be blocking in that particular case is up for debate. It sounds like there is a specific definition of what blocking really is. But to me, if the app is waiting for something, it is blocked, whether it is 10 milliseconds or 10 nanoseconds. The app can still do something while it waits. You may argue that the cost to switch to do something else will be slower than the time the app waits than 10 nanoseconds. However, today I think it's just a technical limitation. This is also true when you read from the socket that has data which copies memory from the kernel to the user space. That's also kind of blocking, right? So I'm kind of arguing also semantics here on this particular podcast as we talk about this. So what do you do if you don't want to wait in line? You send someone who does. We may spin up a thread to perform the blocking read while keeping the main thread block free. The logical read operation becomes asynchronous, non-blocking from a user perspective, but technically speaking, it is still synchronous and blocking to the OS. It is just the thread that is blocked instead of the main process. So we're just playing games. Part 3, DNS. DNS, or domain name system or server or service, is a protocol that resolves domains and host names to network addresses. It is built on top of UDP and more recently on top of TCP and QUIC via DOT or DNS over TLS and DOH or DNS over HTTPS for encrypted DNS. We know how to do socket I/O asynchronously, so you would think DNS would fit right in, right? Because it's just UDP, right? It's just sockets. We know how to do sockets asynchronously. This is true if you rolled out your own DNS implementation. However, most libraries and frameworks and runtimes call the existing OS implementation of DNS, which is get address info. Get ADDR info. This method is synchronous and blocking, and it will require the thread pool trick we did with files to call it asynchronously. Why is it synchronous? Frankly speaking, I couldn't find an answer on the web. But as always, doesn't hurt to guess, because I like to always speculate when things like this. Things like this, when someone just says that, hey, this is me again. When someone just says, hey, this is blocking. It's like, oh, why is it blocking? I don't know. So this is where I come in and try to guess why things are. Because this is where we are right now, guys. We're deep into the weed, So if you're a beginner, you might find this a little bit overwhelming. But I absolutely love this stuff, and I just still feel like I don't understand anything. It's just fascinating the amount of information and things that I learn on a daily basis. Backend engineering is indeed a word. Back to the article. My guess that get address info function isn't just doing DNS resolution via the network, but it might be reading the host's file and getting any user-defined resolution from there. If you remember the host file, at least in Windows, I don't know much about Linux, but in Windows, you can go to C, Windows, System32, drivers, etc., and then host, and you can just add your own DNS resolution entries there. And you can just type in, I don't know, www.google.com, tab, and then 127.0.0.1. And in this case, google.com will resolve to your local host, right? And if you have a web server running there on port 80 or 443, it will just work. It will just point to your website locally, right? Because that trumps anything else. So that's my guess. My guess is that this is actually reading the host file. So it's doing more just the network. So if it's reading a file, then it's definitely going to be blocking, right? And that's my guess here. I know that there is an asynchronous version of get address info function, but it doesn't seem to be used as often. I think it's called get address info _a. Part 4. NodeJS async single thread. Now we go to Node.js. Node.js is a single-threaded runtime, and most of the work is done asynchronously with that single thread. Node.js uses whatever tools available to it through the OS to perform the task asynchronously. In Linux, it uses epoll. In Mac OS, it uses KQ. For Sun OS, it uses event ports. And for Windows, it uses the IOCP, which stands for input-output completion ports. Regardless of the method performed, after the asynchronous I/O is done, Node calls the user callback that are scheduled in the event main loop. Take the TCP server in Node, for example. As developers writing JavaScript code, we never read from connections, right? If you write code in Express or Node, you never actually physically call a read on a connection. Node just gives you data whenever it comes in, right? Through an event, right? You say, hey, on socket data, just give it to me. And if it's an HTTP server, Node does even more job. It actually parses the TCP stream to find request for you and give you a nice request object that is wrapped and, tight and nicely ready for you to use, right? Instead, we listen to an event with a callback function, and whenever there is data, Node calls our function. Behind the scenes, Node is always reading from the file descriptor asynchronously. Now, how this is exactly done, I don't know, but this must be done in a part of a loop, if you ask me. In Linux, it uses epoll, passing the file descriptor, which is the connection, and when the connection has data, the OS notifies Node, which in turn turns around and reads the socket, which calls our function with the data. Of course, when we read the socket, we copy the data from the kernel to the user process, which is Node in this case, and the Node.js will actually call our function. Let me add this part actually to the article. It's pretty cool. I'm actually editing the article as I'm making the audio version here. This is identical to HTTP server and in turn Express.js. Part 5. Node.js thread pool. There are cases where asynchronous ready-based eventing is not possible and where the call must block. Examples are file read-write or DNS lookup, as we explained earlier. If we put the blocking calls on the main thread event loop, Node will block starving other tasks in the process. Node uses a thread pool to address this problem. When a blocking call, example DNS lookup, is scheduled in Node, a thread is assigned that blocking call, and whenever the thread is done, it creates a callback in Node main thread where the next iteration of the loop will pick it up and execute the callback with the result. DNS lookups, file I/O, and user-specified workload can use the thread pool. Some CPU-intensive libraries in Node, such as the crypto library, uses the thread pool too. All this is implemented in the libuv library, which Node uses. Note: Linux new shiny asynchronous I/O, which is called I/O U-ring, is based on completion instead of readiness, and it supports all file descriptors. This is relatively a new technology, and libuv has an open pull request to implement it. It is possible not to use the asynchronous version of read file and opt in for the synchronous version instead. Those calls ends in sync, sync. Example, fs.readFileSync will call the read directly and will block. It will not use the thread pool. Calling this function will block the event main loop. Why would you do that? Maybe you want your code to look pretty. Maybe you are using the threads for some other more important things. Maybe the file you're reading is so tiny that you know it's not gonna cost much. Part 6. DNS lookup bottleneck in Node. As discussed, DNS lookup happens in the background using the thread pool. When calling fetch, the domain in the URL needs to be resolved to an IP address, an IPv4 or an IPv6. So fetch can establish a TCP connection with the server. It could be the case where all the threads in the thread pool are busy, quote unquote, blocked, looking up DNS, which will block the thread pool from doing other DNS resolutions. Or, even worse, asynchronous file I/O, or other crypto operation, or user-defined CPU thread pool operations. That's a little dangerous if you think about it, right? Because if you do a lot of DNS calls, like intentionally or unintentionally, the thread pool might be saturated. Okay? You can, of course, increase the thread pool size. There is a property called uv thread pool underscore size, but once that number exceeds the number of hardware threads on your CPU, it can backfire. And the reason is because the moment you can add any number of threads, right? You can spin up any number of threads, but does that mean your application will gonna get faster? Your backend will gonna be faster? No, because at the end of the day, you have limited resources. The CPU is where the thread has to live to be executed, right? And if you have 100 threads, you're gonna be shifting left and right, moving threads out of the end of the CPU to be executed. And eventually, the cost to context switch between threads is going to be way higher than the cost of execution. And that's bad. That's not on the article, by the way, just me. So Node provides a function called DNS.resolve. DNS.resolve resolves the DNS that always uses the network. And as a result, it is asynchronous. The problem is, how do you know what DNS method your library is using, right? If you're using a library, it's completely a black box. How do you know if it's like, oh, is this like synchronous versus asynchronous? You have no idea, right? This is where leaky abstractions can really bite us. Note, DNS lookup is slightly different from DNS resolving. Lookup indicates that you might have the entry cached locally or might need to read it from the host file. While resolving indicates that you actively do a network call to a DNS resolver to find the result. Guys, I hope you enjoyed this article. I hope you enjoyed this audio podcast. And for members, thank you so much for becoming a member, and appreciate you. I hope you enjoyed this article. If you're interested to learn more about network engineering stuff that I mentioned here, check out my Fundamental to Network Engineering Udemy course. To get a discount coupon, head to network.husseinnasser.com. That's network.husseinnasser.com. network.husseinnasser.com. husseinNasser.com, HUSSEINNASSER.com. That redirects directly to Udemy with the latest and greatest discount coupon. It supports the show. Thank you so much. I'm going to see you in the next one. You guys stay awesome. Goodbye.